Now we'll be looking at another parametric test of difference, the analysis of variance. Before I get into that, I wanted to take a minute to remind you, in case there's any concern and apprehension, I'm not going to require that you complete a analysis of variance or a t-test, or that you could even do that on your own. That's not a requirement. What I'm trying to do is help you to have a conceptual understanding of the ideas involved. But so put your mind at ease. If you're not familiar with statistics and you haven't had any experience with these things, the point of our discussion is to help you to have an understanding of the ideas involved. But you, as I said, you will not be required to compute or even to answer questions about the details of computing these analysis, the t-test and the ANOVA. Not that they are that complicated, really. They're really quite understandable, and I'm sure some of you have even had statistics courses and are quite familiar with this, with these approaches. But I want to put the rest of you hopefully at ease. This is just to help you have an understanding of the concepts. I did want to point out the website you can see here, education.uky.edu/IER. This is a website for the Institute for Educational Research, and right now you can access that website and get some resources and some examples of how you could compute these statistics and various other statistics, and get some other resources on statistics and methods that we're talking about. Then we'll go into a little more detail than I am. So if you're interested in that, go ahead and take a look at that website. Now let's talk about ANOVA, analysis of variance, ANOVA, or how two or more groups differ on one or more variables. There are some similarities between the t-test and ANOVA. Like the t-test, analysis of variance is used to test hypotheses about differences in the average values between two or more groups. However, while the t-test can be used to compare two means, or one mean against a known distribution, analysis of variance can be used to examine differences among the means of several different groups at once. The essential analysis in the ANOVA is whether the differences between groups is significantly different from the differences within groups. This is accomplished by analyzing the variance of each group. We're going to talk through this idea a couple of times, and then I'm going to show you an example visually, and we'll work through that so that you can understand the concept. But basically, within any group or any group that you've collected data, there is going to be variance around the mean. In analysis of variance, the variance or spread of scores around the mean is separated into variance that is due to differences between participants within the different groups, and then variance that is due to differences between all the groups. We examine whether the differences in variance between the groups is greater than the differences within the groups. So the differences in variance between the groups are so great that they must be due to group membership. That's what we're trying to understand. The statistic in ANOVA is called the F statistic. Remember, we used the t statistic, the student's t, when we were talking about the t-test, and the ANOVA, we're talking about an F statistic, which is based on a formula, which is a ratio. It is the ratio of the variance between the groups, as we said, divided by the variance within the groups. The variance between the groups divided by the variance within the groups. So let's look at this visually, what we're talking about. I was thinking we would look at three groups, group 1 is the, I think, blue group. There's blue dots here. So the second group, group 2, will be the red dots, and group 3 will be represented by the yellow dots. So what this is supposed to represent is 3 groups that we have plotted the data for, and it could be anything. I was thinking we could talk about middle school. So this could be like height and weight that we've plotted here of groups in the sixth graders. Let's say the 6th graders are the blue groups, 7th graders are the red group, and 8th graders are the yellow group. Because I've noticed that even though we talk about middle school as one group of students, there's quite a bit of variation in terms of the students' development and maturity. So quite a bit of growth in that 3 years. So this might be a useful way to think about 3 different groups for this example. So I've plotted the height and weight, let's say, for the 6th, 7th, and 8th graders. So what we would do if we wanted to know if there was there were statistically significant differences between the groups is first we would calculate the variance within each group. Remember, variance depends on the mean and the spread of data around the mean. So we would calculate the variance for the 6th graders, the 7th graders, and the 8th graders. And looking at this data, you get the sense that maybe the 8th graders are more different as a group than the 6th and 7th graders, whose variance seems to overlap quite a bit. So it might be harder to recognize that there are actually 2 different groups here than this 8th grade group, which seems to be a more distinct group when we look at the variance of the data there. And then we would also calculate the total variance within the groups. So we would calculate variance within the groups, and we would calculate variance between the groups. And then we would calculate that ratio. To begin calculating the ANOVA, we start with our hypotheses. We begin with a null hypothesis, which states, remember, the null hypothesis states no difference between the groups. So we would say mean 1 be equal to mean 2 would be equal to the mean of group 3. And then our alternative hypothesis would be that the means of the 3 groups would be statistically significantly different, not equal anyway. So the alternative hypothesis is that the means would be not equal. So let's go back to that question of why don't we just use 3 t-tests or 2 t-tests when we have 3 groups, and we could compare group 1 with group 2, group 1 with group 3, and then we could compare group 2 with group 3. So we could do 3 t-tests and see if there were significant differences between them. Could do that, but there's a reason that we don't, and that is that every time we conduct a t-test, the type 1 error would increase. So we're looking at the data, and we did 3 t-tests. Using this data, we would see an increase in our type 1 error rate. So we remember we talked about we typically set alpha at 0.05, and if you do multiple tests on this data, then we would use this formula actually to calculate what our error rate would be. And it's 1 minus parentheses 1 minus alpha parentheses to the power of the number of tests that you do. And if you work that out for 3 tests, then the chances of making a type 1 error, and remember that means rejecting the null when they're actually when it is true. So saying that there are differences when there actually are not. The chances of making a type 1 error would go from 0.05 to 0.143. So we are then much less confident in our ability to avoid making a type 1 error. So that's the problem with doing multiple t-tests, and that's the reason we use analysis of variance when we have more than 2 groups. Now you can use analysis of variance for 2 groups, so it's 2 or more. Alright, so F is the ratio of the differences between the groups to the differences within the groups, as we said. And it's a ratio, and the idea is that if there were a lot of variability in the scores and a lot of overlap, as we saw, for example, between the 6th and 7th graders, then we may end up saying that there is less likelihood that there's a meaningful difference between the groups. And the variability based on group membership was probably more due to chance than to a meaningful difference between the groups. If there's less variability and more distinction between the groups, then our thinking would be when we have more between group variance, more distinction between the groups, then we're more likely to say that there's something going on in terms of being in this group makes you different from being in another group. So there's more variability based on group membership, and so we see more distinction. So because F is a ratio, as the average difference in the variability between the groups gets larger, the F statistic also gets larger. The larger the F statistic, the larger the probability that the differences between the groups is not due to chance but to group membership. So the larger the F statistic, the larger the probability that the differences between the groups is due to group membership. Smaller difference in the variance between the groups, smaller F statistic. So we would calculate our F statistic based on our data, and we would use a computer to do that because it's much faster and easier. As I said, it's not too complicated to do it by hand, but it does require several different calculations, and if you have a lot of data, which you probably would if you were using analysis of variance, right, then it becomes very time consuming. So we would use a computer, and we will look at how to do that soon in this course to calculate the F statistic. And if the F statistic is significant, then that tells us that there are significant differences between the groups we're looking at. But since we have 3 groups in our example, it doesn't tell us how the groups differ from each other. So for example, Group 3 could be significantly different from Group 1 and Group 2, but Group 2 and Group 1 may not be significantly different from each other. So we would know that there was a significant difference between the groups based on our F statistic, but we wouldn't know where the difference lies. And to figure that out, you will see reference to post hoc tests. And post hoc tests, which are tests used to find where the significant differences between the groups lie. And we'll look at that when we look at doing the analysis of variance using the computer software. But I have an example from the literature here. This was based on a study that I did with Michael Frayne at Florida Atlantic University, and we developed a self-management instrument for people with MS. And we were interested in looking at whether people had different scores on our self-management instrument based on how much money they made. So we had different groups based on income. We had some people making more than $4,000 a month, and then some people making $3,000 to $4,000. And so we broke up income groups based on how much people were making each month, and we had about 5 or 6 income groups. So our analysis found that there was a significant difference between the groups. One-way ANOVA revealed significant differences in total MSSM scores based on income. And you would see a statement like that, and then you would see F, and then that in the parentheses there that describes the degrees of freedom equals 4.12, and that F is significant at the p equal 0.001 level. Post hoc comparisons using the Tukey HSD test, and that's just one of the post hoc tests that you can use, and there are different post hoc tests that you might use for different reasons. We use the Tukey in this case, and so our statement was post hoc comparisons using the Tukey HSD test indicated that the only significant differences in the scores based on income were between the scores of those in the two highest income groups and those in the lowest income group. So this tells us that there were some significant differences between groups, but there were also some groups that were not significantly different from each other. So there was a difference between people in the lowest and the two highest income groups, but maybe not between people in the groups in the middle, for example, and the lowest and the highest groups. So if you look at the article, and we make that distinction more clear. But that's the sort of statement that you would see in the research for results of an ANOVA. There are variations of the analysis of variance, including the ANCOVA, the analysis of covariance, and this allows for statistical control of a variable that covaries or varies with the independent variable that might confound your results. So remember, we talked about a confound being a variable that systematically varies with and can confuse your results. So for example, in the study we talked about with different groups, we have a group taking medication for depression, a group taking talk therapy for depression, and a group who are taking talk therapy and medication for depression, and we're interested in knowing whether their scores differ, which approach is most effective. So who has the lowest scores on our depression inventory, for example. So we have three groups, and we want to see if they are different from each other. But let's say that all the people in one group came from one state, Oregon. All the people in the medication group were from Oregon. Let's say all the people in the talk therapy group came from Florida, and all the people in the combined group came from Wisconsin. So you have some sort of variable that's varying with your independent variable like that, and you get your results, and you would want to know whether the results were really due to the independent variable or where the people were coming from. Because people maybe in Oregon are just less depressed or something like that. You would need to understand whether that was a factor in that result. Analysis of covariance allows you to control for this other variable and tells you if your results are based on the independent variable that you're interested in. And then there's also MANOVA, which is a multivariate test, meaning that there's more than one dependent variable. And this is useful, for example, if in addition to depression score, we also wanted to look at some other dependent variable and see if there were differences in the groups based on the independent variable, if there were differences in the dependent variable in addition to depression scores. So let's say we also wanted to know about age differences. So we'd be looking at for differences based on age as well as depression scores. So when you have two dependent variables, then MANOVA can be used. So now we've looked at two parametric tests of difference, the t-test and the analysis of variance. I want to look at next at the non-parametric test of difference that you'll probably most frequently see in the rehabilitation counseling research, and that is the chi-square test. So let's look briefly at the chi-square test. The chi-square test, as I said, is a non-parametric test of statistical significance for bivariate analysis. and the chi-square test is also known as crosstabs. And you'll see that when we do a chi-square analysis using the SPSS computer software. But the chi-square test is a statistical test used to examine differences among categorical variables. So what that means is the chi-square is a test where we compare and try to see if two groups are different based on some categorical variable. The key idea of the chi-square test is a comparison of what we observe in our data and what we expect to see. So it's the difference in the observed and expected values, and how many of something, whether it's responses or number of people in our groups, whatever it is we're looking at, how many were expected and how many were observed. For example, I'm going to walk you through an example to help this make some sense to you. So for example, in rehabilitation counseling, a researcher may want to evaluate whether clients who receive job placement services are more likely to be employed at closure than those who did not receive job placement services. So we have a sample of 40 people. 20 of the clients received job placement services and 20 did not. And we want to know how many were employed at the end of their plan, let's say. So if there are 20 clients who do receive job placement and 20 who did not, our null hypothesis would be that an equal number of each would be employed at the end of their plan. And if we plotted that data in a table, we plotted our null hypothesis expectation in a table, right? Then at the top of the table, we would have the employed group and the not employed distinction. And then on the left side of the table, we have people who received job placement, that group, and then people who did not receive job placement. So we have two groups, 20 each. And in the null hypothesis, no difference between the groups, then we would expect to see 10 employed and 10 not employed among those who did receive job placement, and 10 and 10 among those who did not receive job placement. But let's say we looked at the data that we collected and we found something like this. We found that among those who received job placement, 14 of the 20 were employed and only 6 were not employed. But among those who did not receive job placement, we have the reverse situation. So that's going to work out nicely for our chi-square example. 6 were employed and 14 were not employed. If you looked at the data and you found that, then you might suspect that there was something going on here, that there was some real and meaningful difference between the groups based on whether they received job placement services or not. And we could use a chi-square analysis to tell us whether the difference that we see is statistically significant or just chance and doesn't quite achieve the level of statistical significance. As I said before, chi-square is a non-parametric test. It does not require the sample data to be normally distributed like the t-test and the analysis of variance, those parametric tests do, but the chi-square does have some requirements. The sample must be randomly drawn from the population, first of all. The data must be reported in raw frequencies. So we use counts. We count the data rather than percentages. The categories of the independent and dependent variables must be mutually exclusive and exhaustive. And let's go back and look at what that means. Mutually exclusive means you can only be in one group or the other. So you can only be in the employed group or the not employed group. You can't be in both. So it's mutually exclusive. And exhaustive means all the people are in either one group or the other. So we have mutually exclusive groups, and they are exhaustive. All the people fit into one group or the other. And then finally, observed frequencies cannot be too small. And what that means is that in any one of those boxes, any one of these 4 boxes in which we have data, you can't have less than 5 people. And that has an implication for your data collection and selecting your sample size. If you know that you have to have so many people in order to have at least 5 in each condition, then you can calculate how many you would need to in your sample to meet that condition. So the following minimum frequency threshold should be obeyed. In other words, to do a chi-square analysis, you have to have a certain amount of people in each condition, which is 5, and you can calculate the total number of people you would need in your sample. So for a 2 by 2 table, for example, which we are using in our example, 2 columns and 2 rows, expected frequencies in each cell should be at least 5, so you would need a total of at least 20 cases. 5, 10, 15, 20, 5 for each of the cells in the table. For a 2 by 3 table, so let's look at this table here. We have 2 groups, group 1 and group 2, and 3 different conditions. We have a control group, a talk therapy group, and a meds group. So we have a 2 by 3 table. Then we need at least 5 in each of these boxes, each of these cells. So we would know we need 2 times 3 is 6 times 5. We need at least 30 people to meet the minimum frequency thresholds. So you can calculate that depending on the number of variables you're looking at. For example, if you have a 3 by 3 table, you would know you need 3 times 3 is 9, times 5 is 45. You would need to have at least 45 people in your sample. The basic equation for analyzing the chi-square statistic is this symbol here, the x squared. It represents the chi-square. So that's the symbol for chi squared. Chi squared equals the sum. Remember that sigma represents the sum of the observed minus expected values squared divided by the expected values. And so that is observed minus expected for each cell in our table. So let me go back for a second to our tables. All right, so based on our null hypothesis, we said we expected 10 in each cell. So this is what is expected. What we found, what we observed, is 14 and 6, 6 and 14. So this is what we observed. So to calculate the chi-square, going back to our formula, we would subtract the expected value from the observed value for each of those cells, square it, divided by what we expected, and then we would add those all up. And I'll go through that in just a second. Note that the expected frequency, what we expect to find, can be calculated if it is not obvious. And you can use this equation, the row total times the column total divided by the overall total. But for our expected frequencies, as I said, it's going to work out nicely, as we'll see. So to calculate the chi-square test, we begin with the null hypothesis, which is that the proportions are equal, 10 in each group. There's no difference in the proportions or frequencies between the groups. The alternative hypothesis would be that there is a difference in the proportions or frequencies between the groups, so proportion 1 not equal to proportion 2. Then you would set your type 1 error rate. Your alpha would be set, and we will set it at 0.05. So that's the alpha we'll be using for this analysis. And then we calculate the chi-square. So there's our formula. The sum of observed minus expected squared divided by expected, and we would do that for each cell. For cell 1, we have a 14. That's what we observed. We expected 10, so we would say 14 minus 10 squared divided by the expected 10, and that would equal 4, would be the difference there. We would square that. That would be 16 divided by 10, and we would get 1.6. For the second cell, we have a 6. We expected a 10, so we would subtract 6 minus 10. And again, the difference is going to be 4. We would square that, divided by 10. And so you see, in this case, and this is not typical, it's just the way the data worked out. In this case, we're going to have 1.6 being the value for each equation for each of the 4 cells. So that's the observed minus expected squared divided by the expected. Now we have to sum that. So we sum all these equations for each cell, 1.6 plus 1.6 plus 1.6 plus 1.6, and we come up with 6.4. So our chi-square is equal to 6.4. Now what do we do? Now we would go to a table of critical values for chi-square, and you can just enter chi-square table or critical value table in the search engine, and you'll get a whole lot of options, or you can find a statistics textbook that has a critical values table for chi-square. And we would look and find at the 0.05 level with 1 degree of freedom, and calculating the degree of freedom is simply the number of rows minus 1. So in our example, we have 2 rows, and 2 minus 1 is 1, so we have 1 degree of freedom. So at the 0.05 level, with 1 degree of freedom, the critical value needed to reject the null hypothesis is going to be 3.84, and we would find that in the table. Our chi-square value of 6.4 exceeds that, so we can reject the null hypothesis. Our chi-square is larger than the critical value, so we can reject the null hypothesis, and we can say that the probability is less than 5%. If we did this study, remember that means if we did this study 20 times, then 19 times out of 20 we would not find a difference this large. So it's rare, it's significant that we would find a difference this large if the proportions were equally distributed. So we can conclude that there is a significant difference between the groups receiving and not receiving job placement. So that's an example of how to compute the chi-square. And again, we will also be looking at computing the chi-square on the statistical software in a coming section. But that is how you do it. You can see this one is not too calculated. Too complicated. It's manageable. It's something that you can do on your own with a calculator if you have manageable numbers and sizes of groups. But this is as I said, probably the most frequently used non-parametric test of differences used in the rehabilitation counseling research. It's useful when you have categorical variables. And an example, if you want to see one in the literature, there are actually quite a few. This one was done by Keith Wilson, Deborah Harley, and Reggie Alston in 2001, and they looked at race as a correlate of vocational rehabilitation acceptance rates. So acceptance in voc rehab. So you have race, which was measured as a categorical variable, and so it was either African American or Caucasian. So you have 2 categorical variables. And then you have acceptance, which is also categorical, either accepted or not. So you have a large data set with categorical variables. You can't use the parametric test because our variables are measured categorically. And so in a case like that, you would appropriately use the chi-square test. And this article provides a nice example of that. So that will conclude our discussion of the chi-square and the parametric and non-parametric tests of difference.